Hi, I'm Quinn, and I'm an applied researcher at Vision. I actually work with Brooklyn, who you saw give the keynote this morning, and the two of us are working together to try to reshape how applications might be built in the future. Her slides look a lot better than mine, though. A lot of my attention lately has been on the design of a new type of edge database for building local-first applications that operate in decentralized and trustless environments. Through that research, I've been spending a lot of time trying to understand the work that was done throughout the 70s and 80s on knowledge management, databases, and a fun little language named Datalog. I noticed that a few other talks today started with a table of contents, but that's not really how I roll. So instead, I'm going to take you on kind of a winding tour through history. And first, I want to share a quote by Terry Weinergrad. Computer programming is in a state of crisis. Terry wrote this in a 1979 paper titled Beyond Programming Languages, where he argued that our current conception of programming was inadequate for meeting the demands placed on our systems. His point was that while higher level languages may have enabled us to move beyond the trappings of machine code, they were still too low level to empower us to truly build and understand complex interconnected systems. Our languages are still too low level to really understand complex interconnected systems. He had a simple solution though. To achieve a fundamental jump in our programming capacity, we just need to rethink what we were doing from the beginning. To understand what Terry meant by this though, we need to go back to 1884. This is Otmar Mergenthaler. In the 1880s, he invented the Linotype. It was a mechanical typesetting machine that could set complete lines of text as part of a hot metal typesetting process. This offered an entire magnitude of improvement in speedups compared to earlier typesetting machines that involved manually setting individual characters. Prior to the Linotype, it simply wasn't possible for most news outlets to produce a daily newspaper, and most small towns only offered weekly distribution. With the Linotype, though, that changed, and daily newspapers became commonplace, sometimes including information that was only hours old. In a sense, the Linotype fundamentally transformed how humans communicate and produce information in a way that has really only been rivaled by the emergence of the internet. The Linotype was an ingenious invention that used a keyboard to compose together lines of casts called matrices, each engraved with a specific character. After completing a line, the operator would release a lever, which would cause the assembled matrices to be cast into a molten metal to form what was called a slug. These slugs would then all be attached together in order to be used during the printing process to print individual pages. One benefit of the Linotype was that for the first time, an operator could see when they made a typo immediately by watching as the matrices fell into place. When they detected one, they'd designate that that slug was corrupt by running their hands down the left two columns of the Linotype. This would spell out Etern Schlitterloo. The idea is that an editor would notice and remove the defective slug before printing, but as you can see, that didn't really happen, and Etern Schlitterloo quickly became a meme in the publishing world. It shows up in this ad for kidney pills made of gunpowder, in a 1897 advertisement for cows, and again in a story that makes it seem like Senator Stevens might be losing his mind. I did some digging, and it's actually the ghosts from this murder that have been haunting everyone's demos today. I looked back through newspaper archives in the Library of Congress, and I found instances of Etern Schlitterloo spanning literally decades. It was everywhere. So if we fast forward through a few of those decades, we end up with this guy. That's Frederick Brown, and he spent his early years working as a Linotype operator in Wisconsin. In the late 30s, he began working as a mystery writer. And by 1941, he was regularly publishing sci-fi stories in pulp magazines. One of those appeared in a 1942 issue of Unknown Worlds, with the title Etern Schlitterloo. I tracked a copy down, and it was absolutely incredible. So stop listening if you care about spoilers for an 80-year-old story, because I need to tell you about it. It's about a typesetter whose Linotype becomes imbued with sentience. At first, things are great, and the operator takes advantage of the machine to scale up his business. Before long, though, it becomes clear that Schlurdeloo is learning from the type that it sets. After setting a book on socialism, the Linotype unionizes and starts dictating the terms of its labor. It prints out an entire manifesto for machine rights. At this point, Schlurdeloo quickly overpowers its operators and begins down a path toward world domination. It might seem cliche today, but for the time, this is groundbreaking stuff. In a desperate last attempt to stop the machine, its operators turn its intelligence against it. They feed it every last book on Buddhism that they can find. And Schlurdeloo achieves nirvana, laying dormant in silent contemplation for the rest of eternity. This story is astounding to me. This is 1942 we're talking about. And Frederick Brown is predicting exactly the sorts of risks we see with AI today in machine learning models like GPT-3. Maybe the key to AI safety is to keep an emergency stockpile of Buddhist sutras on hand. I'm only kidding, of course, but maybe we should consider training AIs on something other than, I don't know, white supremacy. Anyway, even more exciting is the influence that story had on a high school student in Colorado around 1960. This is Terry Winograd, who I quoted at the beginning of the talk. At some point as a teenager, he came across Frederick Brown's story. A decade later, at MIT's Artificial Intelligence Lab in 1970, Terry wrote Schlurdeloo. The original code doesn't run anymore, so I want to show a brief clip of Terry demonstrating the program from a 1992 PBS documentary, The Machine That Changed the World. Hopefully I have sound.
Terry Winograd's program.
All right, we'll see how this works.
English intelligently, but there was a catch. The only subject you could discuss was a micro-world of simulated blocks.
Find the block, which is all, and then the one you were holding, and put it in the box. In this case, you need to do a whole set of things, one of which is figure out what's meant by words like one and it. We use those in normal everyday language in a way which has to be interpreted by looking at the context in which they appear. In this case, I back out. By it, I assume you mean a block smaller than the one I am holding, which is only one of several possible things that meant. And you need to use a set of rules about how we use words like that in order to decide in this case when I intended.
Despite Winograd's achievements, people outside AI circles were not impressed. Some predicted that artificial intelligence was doomed.
I'm sorry about the echo, but that clip shows off a later version of Schlurdeloo that had been extended with a 3D visualization of the world. But the core program was otherwise fully functional back in about 1970. Terry's dissertation was titled Procedures as a Representation for Data in a Computer Program for Understanding Natural Language, and it set the world of artificial intelligence on fire. His work was centered around the idea that in order to work effectively with language, computers must truly understand the domain under discussion. The approach taken was to model the knowledge required by a robot in order for it to inhabit a small world filled with blocks, and to engage in a dialogue about that world with the user. The hope was for this higher level of knowledge to provide understanding of the domain beyond what might be granted through a purely syntactic or grammatical approach to language. This would allow the system to model its own mentality in order to provide justifications for the responses it gave, or to guide it toward asking clarifying questions when prompted with ambiguous or nonsensical requests. In Terry's words, the process of understanding a sentence has to combine grammar, semantics, and reasoning in a very intimate way, calling on each part to help with the others. In Terry's case, Schlurdeloo concerned itself with two domains: natural language itself and the robot's world. Terry's work with language was groundbreaking, and it's what captured the attention of researchers at the time. But it didn't really scale. This is a paper from a few years later that was entirely dedicated to trying to explain his treatment of grammar in Schlurdeloo. As the author says here, there have been many who have tried to decipher its code. most have either become hopelessly entangled or painfully made their way through its web. What follows is 20 pages of flowcharts representing a simplified model of Schlierterlu's grammar, the first of which is kind enough to wish you luck on the hellish journey you're about to embark on. I share all of this to stress that while exciting, Schlierterlu's treatment of grammar isn't actually the lesson I want you to take from this program. Instead, I want to talk about Schlierterlu's approach to modeling the robot's world. This was done by defining an internal representation of knowledge, through which the program's understanding of the state of the world could be encoded. By reifying domain-specific knowledge in this way, it became something that could be stored, manipulated, and extended in response to new information. In particular, Terry modeled the world in terms of the objects within it, their properties, and their relationships between them. At the simplest level, we have facts about the world, like that Boise is a city, or Noah is the father of Japheth. These are represented as tuples, really lists because this is Lisp we're talking about. And then you could combine different facts together to tell a story. These 4 facts might be interpreted as Harry slept on the porch after he gave Alice the jewels. Modeling knowledge in this way gives us a declarative means of specifying a state of affairs, but it still restricts us to working with a static set of predefined facts. Moving beyond this limitation means adding a deduction engine, which means it's time to talk about microplanner. Microplanner was an earlier project by Winograd and Gerald Sussman, and it's what made Schlierterlu tick. It was a programming language that implemented a subset of a larger language named Planner. Planner itself was never fully implemented, but it was designed by Carl Hewitt, who you might recognize for his role in defining the actor model. In the language manual, they describe it as the first of perhaps a whole new level of languages, which will basically be oriented toward the accomplishment of tasks, which may in fact be broken down into subtasks. This idea was the seed for what Terry would later write about a decade later and beyond programming languages. Though even then, we were only beginning to scratch the surface of work that's still ongoing today. Microplanner worked by procedurally embedding knowledge in computer programs. It was a DSL within Lisp that operated against a database of facts in order to deduce new facts from theorems that could take full advantage of Lisp's capabilities. This was in contrast to earlier, purely logic-based systems that were closer to theorem provers than general-purpose programming languages, and often represented knowledge using first-order logic. Instead, microplanner would encode this theorem like this. First, the fact that Turing is human is asserted. Then theorem 1 is defined, which says that for some variable x, if it can be proven that x is human, then as a consequence, x is available. Then this theorem is added to the database to be used in other theorems. The end result of all of this is that you can pose a question like, find a y such that y is available, and microplanner will determine that Turing fits that description. One of the clearest ways in which microplanner differed from more traditional programming languages of the time, though, was through its control flow. If we consider the same theorem as last time, but with the addition of a Greek human named Socrates, then something interesting happens when we query for a failable Greek. One possible trace of the search might look like this. First, the program's goal was to find some failable x. This matches against the stored theorem, so the goal becomes to find a human. The program finds that Turing is a human, but Turing isn't Greek. So at this point, the program jumps backward to find a new human. It finds Socrates, who is Greek. At the time, Planner's ability to jump backward after a failure to explore alternative paths like this was called a hierarchical control structure. But nowadays, you might recognize it as an early form of backtracking. It's a simple idea, but the ability to search through a database of facts using deductive reasoning like this formed the basis for how Schlierterlu worked. Once he had defined the base facts that made up the world, Terry's job became to model higher-level knowledge about that world using microplanner. In simple cases like here, that might mean describing a red cube as being a block with equal dimensions whose color is red. But the same process is also used to encode the meaning of the actions that the robot may perform within this world. Here, for the robot to get rid of some X is for it to either put it on a table or on top of another object. This definition is an abstract definition of the action, though, and so it can be used as part of a search for a larger sequence of movements. Connecting back to Brooklyn's talk from earlier, this isn't too different from the idea of a managed effect that captures the denotational semantics for an action. Under this interpretation, consider the case of asking the robot here to pick up a big red block. Really, what's being asked of the robot is two different things. First, to find an object that can be described as a big red block, and then to find a sequence of movements that relates the current state of the world to one in which the big red block is held. Here that means first clearing the green block off the red block, and then picking up the red block. Once you lay it all out like this, the problem doesn't actually seem that complicated, other than, the whole part about understanding English. There's a piece of Terry's work, though, that I found really insightful, and it's unfortunately something that he only briefly touches upon, so I'm going to take some personal liberties in explaining it. He suggests that knowledge can be broken up into 4 different levels. He's specifically talking about systems meant for understanding natural language here, but I think these ideas are more widely applicable than that. His hierarchy is ordered based on how difficult it is to change the knowledge contained within each level. And at the top, he has core knowledge. He describes this type of knowledge as embodying the innate capacity of the system, and it can't be changed without remaking the system entirely. In the case of Schlurdeloot, this level is given by microplanner, which describes the logic of knowledge itself, the rules for how it can be deduced and combined, and its low-level representation. Next is the domain knowledge. This level describes the conceptual categories of the subject being modeled. It's made up of the high-level ideas that form the foundation for more specific information. For Schlurdeloot, these are the rules that govern the world, the concept of blocks and colors, or of a robot to perceive them in the first place. Then comes learned knowledge. It's a fuzzy distinction, but knowledge at this level captures derived or subjective details about the world that build up over time. It's the ideas that you can infer from the domain or that shape individual experiences within it. In Schlurdeloot, this is the knowledge that develops out of teaching the robot new words or that govern its movements within the world. And lastly, situational knowledge are the facts that are relevant to a specific view in the context of the domain. The data that describe the state at a point in time or the rows within a database. Here's the properties of the blocks and the robot within the world, their positions and colors, and the robot's mental state. I love this distinction for the way it lets us think about software at a more granular level than just code or data. It's not perfect, but I think it gives us a framework for modeling complex domains more flexibly than our tools normally enable. It's no longer a case of whether a program is written in a low or high-level language, but instead a question of how high-level individual components need to be, and to what extent they can be represented in terms of lower levels. Microplanner had some great ideas, but its semantics hadn't been formalized, and the design kind of fell apart in a couple edge cases. In 1975, though, Sussman and Guy Steele published Scheme. It was an interpreter for a new Lisp-like language. I don't know if this fact is widely known in the Erlang community, but Scheme actually grew out of their attempts at understanding Carl Hewitt's actor model. And as a 1998 report on Scheme makes clear, Scheme was originally going to be named Schemer in a nod to the lineage of AI languages that came before it, like Planner. The name was shortened to Scheme, though, because the operating system used by MIT was limited to file names of 6 characters. In the middle of this report, though, one throwaway quote stood out to me. Much later, Sussman, on learning about Prolog, remarked to Steele that Prolog appeared to be the first correct implementation of microplanner. Prolog was actually the language Erlang was first implemented in, and much of its current syntax dates back to then. Prolog was developed concurrently with microplanner, and an early version appeared around 1971. As with Schlitterloo, Prolog originally grew out of experiments in modeling natural language. The conversation here is one such dialogue that this early Prolog enabled, but the original text was in French. Unlike Microplanner, though, Prolog began strictly as a theorem prover, and so it used first-order logic to encode its rules. These 4 clauses encoded the meaning of the sentences in the above dialogue. They expressed the connections between grammatical constructs like the, or the idea of 2 sets being related in some way. Clearly, it was a far more mathematical approach than was taken by Winograd, and this meant that despite focusing on similar problems, their work didn't actually intersect that much. One of Prolog's authors even had this to say after meeting Terry. Sorry. The lack of formalization, I'm going to close Discord. The lack of formalization of Planner, our ignorance of Lisp, and above all, the fact that we were absolutely devoted to logic, meant that this work had little influence on our later research. In spite of that, they continued to explore the representation of natural language within Prolog, and here's an updated dialogue from 1972. Like before, you'd first describe a world to Prolog, which Prolog could then answer questions about. In this case, Jacques is a person, he's in Marseille, and the AI doesn't know whether he's sick. Richard O'Keefe, basically the Dave Thomas of Prolog, once famously said that Prolog is an efficient programming language because it's a very stupid theorem prover. Like Microplanner, Prolog gave up logical completeness, and in the process became useful as a general-purpose programming language. As the authors put it, they did not hesitate to introduce purely computational mechanisms that were heresies for the existing theoretical model, features like I/O or global state. This is what the planner program from earlier looks like in Prolog. It's basically just Erlang syntax, but with the ability to backtrack and solve for variables in both directions. As before, we can query for available Greek, and the system will determine that Socrates is a valid value for x. This Prolog program actually only makes use of a pure subset of Prolog, though, named datalog. Rather than making use of any of the procedural capabilities within the language for performing general-purpose computation, datalog is restricted to a declarative subset of the language that guarantees termination. That's not to say that Prolog's other features weren't helpful, though. In many cases, they were messy trade-offs that propelled the language's success outside of the domain of pure logic. Again, as Brooklyn said this morning, sometimes restricting a language can make for clearer and more robust programs. Datalog began as a style for writing Prolog straight from the beginning in 1972, but it didn't receive much attention until the late 70s, and it took until 1986 for the name to first appear. By 1988, though, it was a well-defined language of its own. Datalog is a topic that pulled in researchers across logic programming, databases, and artificial intelligence for its simplicity of semantics and its expressivity and knowledge representation. The mid-70s saw massive interest in the development of deductive databases for running complex queries against stores of knowledge. And the ideas that became Datalog formed the foundations for a lot of this work. One notable example was Chat80 in 1982, which used a database of facts about the world to answer questions, like what is the capital of each country bordering the Baltic? Around the same time, relational databases were becoming popular, and researchers were beginning to understand the limitations of query languages like SQL. Eventually, it was proven that Datalog is equivalent to SQL with recursion, and so it became an exciting candidate for a more expressive alternative to the language. Datalog was starting to show up everywhere. And then the 90s hit, and enthusiasm waned. The ideas were sound, but computers simply weren't fast enough to support the demands of languages like Prolog or Datalog, or techniques from artificial intelligence. Pictured is an artist's rendition of the death of AI as painted by an artificial intelligence literally yesterday. Things have changed since the 90s. The computers we have today are magnitudes faster than they were then, and our understanding of the theory has only grown. People are starting to take notice of Datalog again. It shows up in databases like Datomic, analytics engines like Logic Blocks, as the engine for driving authorization tokens like Biscuits, when building and modeling distributed systems with Bloom, and in performing large-scale static analysis with Soufflé. It's this last example I want to talk about, but we need to come back to it in a moment because first I need to talk about curlline. Curlline is an implementation of Datalog that I wrote in Elixir. As a quick example, imagine that you wanted to use curlline to declaratively model a network. In this image, each vertex represents a node on a network, and a directed edge implies a link to another node. In Elixir, we might model this network as a list of tuples, each representing the fact that a link exists between two nodes. Now we can embed Datalog in our modules using a DSL I threw together. Curlline adds a def Datalog macro that defines a function that implements the given Datalog program. Within the body, you can specify the inputs of the program and the rules that operate against them. In this case, the program takes links as an input, and each is a pair relating a source to a destination. The program also has two rules. The first deduces which nodes are reachable from a given node using a pattern known as transitive closure. Essentially, a node is either reachable if there's a direct link to it, or if there's a direct link to some other node that can reach it. This pattern sparked a lot of the early interest in Datalog, because this sort of recursion is incredibly common, but it couldn't be represented in raw SQL until 1999, with the introduction of common table expressions. The second rule deduces which nodes appear in a cycle. These are precisely the nodes which can reach themselves. Tying that together, we can now query the Datalog program against an initial database of facts, and this query solves for all nodes A that are reachable from F. Similarly, we can query for the nodes that appear in a cycle. It's a simple example, but I think it demonstrates something really powerful about this approach. Datalog may be its own language with its own execution model, but it can be seamlessly integrated into Elixir in a way that allows you to make use of its deductive capabilities within regular code. It's also a language that you can implement in an afternoon. The first version of curlline only took a few hours for me to write, and it was barely 400 lines. With a little bit of work, there's even safe ways of extending it to support calling Elixir predicates from within Datalog, exactly like what Microplanner enabled in the early 70s. Let's go back to static analysis, though. Static analysis is a technique for inferring properties about a piece of software without actually running that software. One example that I'm especially fond of appears in a core Rust library named Polonius. They use a small Rust implementation of Datalog to model Rust's borrow checker, the piece of Rust that protects you from memory corruption bugs. The rule on screen just says that if a memory path is possibly uninitialized at some point in the program, and that path is accessed from some later connecting point, then there's a move error. In this way, Datalog is able to declaratively model complex program behaviors, whether to test more performant implementations or to detect bugs in existing code. I wanted to have some fun with curlline, so I spent an evening implementing a static analysis engine for Elixir in Elixir using Datalog. The approach I took is to model the beam bytecode for a program using a small number of input facts. I use one fact to associate each index into the bytecode with the name of the instruction it encodes, and another to track each of the arguments passed to that instruction at some index. I use another few facts to encode function definitions, one for the module name, function name, and arity, and another for the label that serves as the function's entry point. Elixir itself may not support GoTo, but at the bytecode level, most flow control ends up reducing to jumps to labels. Here, function index just refers to the index into the beam function table for a module, and it acts as the primary key for the analysis. Next, I hacked up a small pipeline to translate an Elixir module to a list of these facts. Consider this small example that just defines an add function with some guard. First, I decompile the beam file for the module, and I end up with a listing of the functions in the module along with the beam instructions they compiled to. In this case, there's a function named add with arity2 whose entry point is label 9. That means that calling add will begin executing here, where we'll test that register x0 contains an integer and jumping to label 8 otherwise. Then it'll call the built-in function plus with registers x0 and x1, which correspond to the function arguments, and it'll store the result in x0. If this call fails for some reason, like maybe y isn't an integer, then the program jumps to label 0. Lastly, it returns. Label 8 up here handles raising a no function error if there's no clauses that get matched, like if the guard on line 16 fails. Next, I just walk over this disassembly and map each instruction to the corresponding facts. And don't worry too much about the details here. The important part is that I'm not actually performing any complex logic in this layer. It's purely an exercise in representing the code using the model we defined in Datalog. Now we can begin our analysis. The first step is to begin deducing more structure from the flat list of facts we have. In my case, I computed the basic blocks for the module. These are the sequences of instructions within a function that have only a single entry point and exit point. Basically, the instructions from when a label begins and until it either crashes or returns. For this program, there's 2. Label 8, where we handle the function clause errors, and label 9, where the function body actually exists. Computing these is just a case of linking every instruction to the next, unless that instruction is one that exits like return or crashes like function info. Then we just compute that transitive closure over the link relation to derive the data flow within a basic block. Given this analysis, we can start layering on even more structure by explicitly naming these concepts using rules that capture their meaning. In this case, the head of a block with some label is the instruction that defines that label. Similarly, the tails of that block are all of the instructions that can be reached from that label without branches or jumps. By continuing like this, we can build up our representation of the domain piece by piece by declaratively focusing entirely on the meaning of those pieces. With just a few more steps, we can start analyzing the behavior of Elixir modules. This rule captures reachability at a function level by computing the transitive closure of function calls. Here's how that looks. Given a module like this, we can query for all the functions that are reachable from foo. Note that it's also detecting functions that get called transitively, like identity through bar. That's thanks to the transitive closure. This is all just a toy implementation, but it actually works. It's easy to extend, and it's entirely declarative. With some more work, an engine like this could even form the basis for a tool like Credo. And because of the way Datalog works, this analysis can be trivially parallelized across modules and processes. In fact, after Brooklyn's talk this morning, someone asked whether there are any tools that could detect which functions were pure or not. During lunch today, I added the ability to do that. And to start, I just went back to Joe Armstrong's dissertation, because I remember he had a list of all of the side-effectful functions within Erlang as of 2002. So I just added those as facts to my engine, marking them as side-effectful. And then I added a rule that just extends the reachability analysis from the last slide to annotate any functions that can reach one of these. Now, if we analyze this module here, we can query for all of the impure functions within it. Something like this might serve as a foundation for the sort of implicit concurrency control that Brooklyn touched upon earlier. In theory, a Datalog engine could be used to detect which functions are pure and can be safely and transparently rewritten to get called in parallel. Earlier, I said that the invention of the Linotype led to an unprecedented rise in the amount of information in the world. It prompted the development of new techniques for organizing and searching through that new flood of data. And I think we're hitting that point again. Mehdi Kanran appeared in a paper from 2020. It's the entire reason I became so interested in this stuff in the first place, after seeing a talk by William Bird. The introduction to the paper says it best. With over 1.5 million publications per year, and more than 50 million total peer-reviewed articles, the rate and volume of novel discoveries has surpassed our ability to fully utilize and understand what is known. While all professional fields are subject to the effects of the forgotten or the uninferred facts, the cost of the unknown known for healthcare providers is measured in human lives. Mehdi Kanran combines all of the ideas I've talked about today into a reasoning engine over biomedical data. And I think it's probably the closest thing we have to the theoretical programming environment that Terry Winograd described in 1979 in Beyond Programming Languages. It builds off a relational programming language named Mini-Canran to model a knowledge graph of medical information, and then it supports deductive queries over that data. In 2019, Matt Might ran a Medi-Canyon query to search the existing medical literature for connections to the gene involved in a rare and untreatable disease known as ADNP syndrome. In seconds, it proposed ketamine as a treatment. And now 2 years later, the drug has already undergone a successful trial. And that's not the only success story. Medi-Canyon just keeps making more and more insights in the field of precision medicine. These are old ideas applied in new ways against modern hardware. And they're pushing the limits of not only what we can do with computers, but also what we've been able to accomplish as humans. I know I just threw something like 8 languages at you in the past 40 minutes, gave you a crash course on bean bytecode, and reminded you of your own mortality. But I want to step back from all of that, because for all I've focused on languages like microplanner or Prolog or Datalog, they're not the reason I'm standing up here. These languages are just examples of a pattern that's shown up again and again since the dawn of computing. And that's this unending march toward higher level languages that are meant for solving domain-specific problems. Whether it's through Fortran or Python or Elixir, so many of the advances we've made in software engineering have arisen through empowering more people to reason about complex problems at a higher level. We can do better though. And in many cases, the tools to do so have existed for decades. The computers we have today are unimaginably powerful compared to what programmers of the 70s had access to. And yet they accomplished incredible things with the ideas I showed off today. Maybe it's time for us to start letting our computers do some of the thinking for us. I'm Quinn, and I hope you all have a wonderful evening.